thermodynamics.com.
Okay, students, now we are going to complete the thermodynamics in one shot. Okay, it is highly useful for the preparation during the last moment. In the last moment, if you wanted to complete thoroughly and within a short span of time, this is the best way to complete your thermodynamics. Okay, let's start. Okay, students, thermodynamics. Overall, whatever the topic we are going to study, these are the topics we are going to study in the thermodynamics. Okay, so first, what is thermodynamics? Definition of thermodynamics we will study, and second, zeroth law of thermodynamics, first law of thermodynamics, thermochemistry we will try to cover separately because this is the most interesting part of the entire thermodynamics. Okay, then second law of thermodynamics and third law of thermodynamics. Okay, these are the topics we are going to cover. Thermodynamics mainly zeroth law, first law, second law, and third law of thermodynamics. Okay, this is our strategy to complete it. So let us start with one by one. First of all, what is thermodynamics? It is a branch of science which deal with different form of energy. It can be from any form, but it should be converted into which form? Heat energy. Okay, heat energy to different forms and different forms to heat energy. Okay, so that branch of the chemistry or branch of the science we can say, because this you are going to study in physics also. Okay, so thermodynamics is a branch of science which deals conversion of different form of energy into heat and heat energy into and different forms. Okay, so they follow, once they are interconverted from one form to another form, they must follow either zeroth law or first law, second law, or third law of thermodynamics. Okay, this is the introduction. Now let's start one by one. Okay, once you start anything, first of all, you should know the very basics and what terminology you are going to use over there. So let us know about the terminology. Okay, before starting, is there any use of thermodynamics or not? Okay, in chemistry, especially I am talking about in chemistry using the thermodynamics. Okay, first we can predict feasibility of the reaction. If two substances are mixed, then reaction between them will take place or not. Okay, predicting means deciding before itself. Before doing anything we can predict. Okay, this match is going to be wonderful, or this picture is going to be wonderful, or this day is going to be wonderful. Like that you are predicting. It is not yet happened, but you are deciding, you are assuming that this is going to be good. So that is what predicting. Okay, feasibility means it is nothing but just possible, whether a reaction, instead of carrying out and losing our energy, losing our money and everything, by using the thermodynamics, we can, before starting of the reaction itself, okay, before starting of the reaction, whether that reaction is possible, whether that reaction will occur or not. Okay, if we wanted to make it happen, then what is the temperature we need to maintain, what is the pressure we need to maintain, that all we can predict before the reaction starts. Okay, then if the reaction does not takes place, then energy change involved during the reaction. Okay, if the reaction does takes place. Okay, not only predicting whether this will happen or not, then if it happens also, what is going to be the energy changes. Without carrying out the reaction, first thing we can identify whether that reaction will takes place or not. If it is taking place, then what will be the energy required or released. If released, how much energy released. If required, how much energy is required. Okay, then if a chemical reaction is in equilibrium going to attain, then what will be the equilibrium concentration also. Okay, equilibrium concentration also we can calculate by using the thermodynamics. These are the uses of thermodynamics in the chemistry. Okay, this is about the uses of thermodynamics in the chemistry. Even though we have great uses, but there are some problems. Okay, there are some limitations. What are those limitations? Law of thermodynamics are applicable to matter in bulk on or a system as a whole. Okay, it will not give about the individual molecules, it will not give about the individual particle. They can be applicable only bulk, like temperature of system, pressure of system, enthalpy of system. Okay, so it is applicable in bulk. Bulk in the sense large quantities. This is applicable only specially when the things are in large quantity. Okay. Then second, thermodynamics cannot calculate time taken. Okay. It will give you how much energy will be released. It will give you how much energy required, but it will not give you how much time it will take to complete the reaction or how much time it required to reach the equilibrium. These are the two limitations. First limitation is it will not tell you about the individual particle. It will talk about the entire system or bulk. Okay. Second thing, it will not give you the time required, whether the reaction is fast or slow. Okay. For this purpose only, there is again special branch is given. What is that special branch? Chemical kinetics. Okay. Chemical kinetics will give you time taken or whether it is a fast reaction or slow reaction, whereas thermodynamics will give you how much heat is required or how much heat will be released. Okay, that is about the thermodynamics disadvantages, you can say, or even you can say limitations. Okay, so I think all of you noted this. Okay, as this is a separate branch, special branch. So special branches will have special portfolios, special terms. Okay. So like here also we are going to use some special terms. Okay. So what are those terms? System. What is the first word we are going to use? We are going to use a term called as a system. Okay. Here it is not the system means something else. Here system means the part of universe under study for energy changes. Okay, we are studying in a test tube. Suppose we have taken a test tube and we are giving heat by heating it, or by heat is evolved from the test tube, then the test tube will become as a system. Okay, it is a part of universe which is under study, which is under observation. So this got the different meaning. Okay, so system outside it is different, and in the thermodynamics it is different. In thermodynamics, if I say system means, don't think like that it is a computer. Okay, like when you go for a cyber cafe and you ask for whether a system is free or not, that means computer is free or not. Or when you go to the organization and ask what is the system to apply the for admission, that is different. Here system means it can be any part of the universe which is under study. Even suppose you are studying from the book, so that book will become as a system. Okay, you are playing a game in mobile, then that mobile will become as a system. Whichever is the part of universe which is under observation, which is under study, it is called as a system. Okay, suppose air in a room, water in a bottle. Here bottle will become a system, room will become a system. Okay, or any living in body. Okay, so these are the systems. Body also will become a system, bottle also can become a system, room can also become a system, because we are studying about them. Okay, everything other than the system in the universe is called as a surrounding. Other than the system in this universe, whatever the things are there, they are called as a surroundings. That means we can say universe is equal to system plus surrounding. Universe is equal to what? System plus surrounding. Like this is a system. Okay, this is total universe. So if I exclude this part, okay, if I exclude this part, I will take another color. So this red color portion, red color line portion will be what? Surrounding. Blue color line portion will be what? System. and the entire including system and surrounding, this is called as what? Universe. Understood? The biggest part is universe, then it is surrounding, then it will be system. This is about the size I am talking about. Okay, universe is larger than surrounding, then system. Okay, so this is about the terminology we are going to use. So before going to use, you should know the proper utilization, proper meaning of that words. Okay, so this is about the terminology we are going to use. Okay, now let us see the another part. Okay, next, boundary. Very, very important topic, especially those who wanted seat in the NITs, those who wanted seat in the AIMS. Okay, for them it is must read topic. Okay, so first, boundary. Boundary means anything which separates system and surrounding. Okay, like in the previous diagram I have shown with the square. So that square is called as a boundary. So up to here it is system, outside this is surrounding, and this is a universe. Okay. So boundary can be real or imaginary. It is not that we will see the boundary. No, it is not like that. It will be sometimes imaginary also. Okay. Boundary can be real or imaginary. Boundary can be real or imaginary. Boundary can be flexible or rigid. That means you cannot change its shape, or you can change its shape. Understood? Next, like air in a flexible balloon. So that means it is a flexible boundary. Air in a room, that is a rigid boundary. Okay. Next, boundary can be adiabatic. Adiabatic means heat cannot flow. Okay. So non-conducting, that means the heat of the system. Heat inside the system will be constant. Heat in the surrounding will be constant. Okay. So this is very most important word. We will be using this in the numerical solving. Okay. So once boundary is adiabatic, that means it is non-conducting. Whenever they say adiabatic boundary, that means you can say in the formula, you can substitute delta Q is equal to 0. What you can substitute? Delta Q is equal to 0. Second thing, diathermic. Just opposite to the adiabatic is diathermic. Okay. It is conducting. So heat will keep on flowing. But till what time the heat will keep on flowing? Till the time temperature is same. So I am taking, let us take I'm taking, this is a system and these are the diathermic. Okay, what is this diathermic wall? Okay, and here it is 30 degrees Celsius and outside it is 20 degrees Celsius. Okay, so this is what surroundings. What is this surrounding? This is what system. Okay, so the diathermic walls are there. These are system and this is surrounding. Okay, what is this? This is surrounding. Now heat will flow. Heat will flow from 30 degrees Celsius to 20 degrees Celsius because heat always flows from high temperature to low temperature. But till what time it will flow? Till the time this temperature is reduced and becomes as 25 degrees Celsius. This temperature will increase and becomes as 25 degrees Celsius. Okay. Once both system and surroundings reaches up to 25 degrees Celsius, the heat will flow. So that means delta Q is not equal to 0. Flowing outside means somewhere heat is reduced, somewhere heat is increased. If I talk about the system, here heat is lost by the system, and talk about the surrounding, heat is gained by the system. So delta Q is not equal to 0. But delta T is equal to 0. That is difference between the system and surrounding. Temperature is now 0, 25 and 25. Okay. So whenever they use a term diathermic wall, what you will substitute? Delta T is equal to 0 and delta Q you will be given. And if it is adiabatic wall, delta Q you will substitute as a 0. Okay. So this is about the what? Boundary. Boundary can be real or imaginary. Boundary can be flexible or rigid. Boundary can be adiabatic or diathermic. Type boundary means anything which separates. Up to here it is system. After this, this is going to be surrounding. Then it is called as a boundary. Okay. So let us see the next slide. Next, types of system, very basic thing. Okay, so this is not important as it is, but whatever the topic we are going to study, to understand them, this is going to be very important. Okay, so if you don't know system types, then you cannot understand a single word from now onwards. That's why it is very basic. Okay, so open system. Okay, what is the first term we are going to study? Open system. Open system is the system which can exchange energy as well as matter both with what? Surrounding. Okay, so let us imagine a cup of tea in the cup. Okay, what is this? Cup of tea in the cup? And anyhow, I will be giving you a wonderful diagram afterwards. But now it is open. So here, if you keep it open, then heat will be given by the system to the surrounding. So that means exchange of energy is there. Some vapors are going out. Therefore, matter is also lost by the system. So open system is the system which can exchange energy as well as matter, like air in open room, water flow in the pipe. Okay, or living system, any living system is, you will maintain the temperature outside the temperature. Okay, next, closed system which can exchange only energy, but cannot exchange matter. Okay, so it cannot reveal the matter, but it can exchange the happiness. That's all. Understood? Happiness or sorrow. If we are asking why is he happy or sorrow, then you will tell happy or sorrow. But what is the reason for that? Matter will not be revealed. Okay. So the system which can exchange only energy but not matter with what? Surroundings is called as a closed system. Suppose the same cup, now it is closed with the lid. Okay, but that lid which can exchange energy, but that lid is what? Diathermic lid. Okay, so once it is a diathermic lid, then heat can go out, but the vapors cannot go out. That means that is a closed container. Any matter in a closed container. Okay, heating of a water in a closed container. So that substance which is stored inside the container will not go outside, whereas the heat will be dissipated. Okay, how many ways of heat dissipation is there? That also we are going to study. Okay. Next, isolated system, very peculiar system. It cannot exchange energy, it cannot exchange matter, nothing, everything is separate, isolated. Okay, so like tea in a thermos flask or water in a thermos flask. Okay, so this is completely isolated, neither heat can go out nor substances can go out. Okay, so that is called as isolated system. And very important thing, all of you will remember and write 5 times if required. The whole of the universe is a perfect isolated system. Whole of the universe is perfect isolated system. Okay. So this is about the types of system. Types of systems are basically how many types? 3 types. Open system can exchange all, including energy and matter. Closed system can exchange only energy but not matter. Isolated system cannot exchange heat, cannot exchange matter. Okay, that is what the types of system. Now let us see a beautiful diagram for the complete clear explanation. Okay, so this is what the complete explanation by Wijchem. Okay, see here, this is system and this is surrounding. Matter can be exchanged, energy can be exchanged. Okay, so this is called as a open system. This is surrounding, this is system. Double arrow means heat can come into the system, heat can go out from the system. Okay. So with the out means it is going into the surroundings. Understood? Now let us take the closed system. In the closed system, which is permitted? Which is permitted? Matter is not permitted. Energy is permitted to exchange between the system and surrounding. System and what? Surrounding. Okay. And if matter is also not permitted, energy also not permitted, then it is called as an isolated system. Okay. So this is the complete diagrammatic explanation for clear visualization of the things. Okay. So here both are permitted. Here matter is not permitted. Here matter is not permitted. Energy is not permitted to exchange between the system and surroundings. System and surroundings. Is it understood? Okay. So I think clearly noted. Now let us see about the next one. Next one is state of a system. Okay, next topic, what is that? State of a system. State of a system is the condition. Okay, so what is your state? That means are you healthy or not? Like as a human being, if somebody asks what is your state now, are you healthy? Okay, then like that, if you ask to the system what is its condition, that condition is expressed in terms of the state. Okay, it is specified by like are you healthy or not. We can measure their healthiness with the help of the temperature, with the help of the glow in the face. Okay, same way, but for a system, it can be specified or defined by measuring some observable, measurable properties. Okay, like temperature is a measurable property. Okay, like what to define state of a system. To define state of a system, some measurable properties are need to be explained. The system is at 1 atm pressure in a 2-liter container at 27 degrees Celsius and 2 moles of substance. Okay. So like these are all required to explain about the state of a system. Okay. So what is the state of nitrogen gas? If somebody asks what is the state of the nitrogen gas, then what you will say? The nitrogen gas is at 1 atm pressure in a 5-liter container at 27 degrees Celsius and it is 1.2 moles. Okay. So let us take this is the 1.2 moles. So these are the things which are explaining about the state of nitrogen. Okay. So these are the measurable properties which need to be explained, which need to be explained to explain the state of the condition of the system. Okay. Other than this, for the chemistry purpose, I told, and in the physics also, it can be elasticity, it can be heat capacity, lot of things. Okay. So like gaseous system, what are the required? Volume is required for specifying the condition. Temperature is required for specifying the condition. Pressure is required for specifying the condition. Okay. So you may specify more properties, but it will become complex. What it will become? It will become complex. Okay. Okay. Next, there are two types of function: path function and state function. Very, very important topic, and most of the time questions will be in more than one correct or single correct. Okay, which of the following are state function, which of the following are uh, path function? There are two types of functions. Okay, first one is state function, second one is path function. Until unless you don't understand the original meaning of this, it will be very difficult to understand further concepts. Okay, so let us see state function. Okay. So try to understand meaning instead of by hearting. Instead of by hearting examples, if you understand the meaning, you yourself can identify whether it is a state function or path function. Okay. So the property of system which depend only on state of the system. Okay. at a point function is called as a point function. Okay. Suppose now what is its state? Earlier what was it? It is now not varied. Okay. So if somebody asks he is a good person or bad person, now then what you will say? He is good to me. So how he is treating you is only the state function. No, he was not good person in the last 3 days or last 1 year. Before 1 year he was not good person. That time it will be path function. Okay. Presently what is the state? Presently only if it depends, then it is called as a state function. Okay. It is independent of the path adopted. Understood? Suppose your parents are asking what are your marks. If you say 98 marks out of 100, okay. So if they are worried only about you got good marks, then it is a state function. Okay. Now if they start asking, no, I think you have cheated the examination. It is not your original marks. Okay. Then it will be a path function. Okay. If they are worried about only your marks, then it is state function. If they worried about how you attained that much marks, then it is called as a path function. Okay. Supposing displacement of an object will be a state function, but distance will be path function. Okay. Suppose from here A to B. Okay. This is point A and this is point B. So this much only the change in their position. That is called as a displacement. So it is not worried how it reached from A to B. So if it is reaching from A to C, C to D, then to B, this is called as distance. So distance is a path function, whereas displacement is a state function. Okay. So in thermodynamics, state functions examples: temperature, pressure, volume, total internal energy. This is very important. Total internal energy you have to identify. If I say delta E, that is not a state function. If I say internal energy, total enthalpy, total Gibbs free energy, total entropy, all are state functions. Okay. They do not depend on the path they achieved. Okay. So this is about the state function. Okay. Now let us see about the next topic, that is path function. Okay, what is that path function that we are going to check it now? Okay, suppose if you take as a cyclic process, if you take a cyclic process, okay, then state function must be zero. State function must be zero because it is going from 1 to 2, but it is coming back to the same state. So initial state and final state are zero. Okay, so they both are same. Therefore, state function will be zero. State variables are extensive, can be extensive or intensive. Extensive, intensive, we are going to study, or I will tell here itself. Extensive or intensive. Extensive means which depends on quantity, which depends on quantity. Okay, then it is called as a extensive, which does not depend any property, which does not depend, which does not depend on quantity, which does not depend on quantity are called as intensive. Okay. So for that also I will give an example. Don't worry. If it does not depend on quantity, then it is called as intensive. If it depends on the quantity, then it is called extensive. Okay. See, whatever I told you, total temperature is a state function, but change in temperature is a path function. Change whenever this delta comes, then it will not be a state function. Okay. So because of this small misconcept, people are losing so many marks. So I don't want you should be one of them. Okay. So let us go for the next slide. Okay. Next, path function. Okay. Now, path function, quantities which are dependent on path, how they have attained, how it is possible to get so many marks. Either he worked hard or he made some malpractice. That also, if they are worried, then it is called as a path function. Okay, heat energy, work energy, and heat capacity. These are the path functions. These quantities defined when there is a process is going on. Okay, heat transferred, heat work done. So these are the process. So how much work is done and which way it is done, so that way also we are worried. Okay, so they cannot have any definite particular value in any particular state of the system. Okay, so there are not, heat energy is not fixed. If the process is carried out isothermal, then delta T will be something else. If the process is carried out adiabatic, Q will be different. Like that, that depend on the process, how it is carried out. Okay. If we carry out the same process in different methods, different will be heat, different will be work, different will be heat capacities. Okay. So this is about the path function definition and its examples. Okay. So let us see the next one. Now, extensive and intensive, already I told you, just let us revise it, okay, thoroughly. Extensive, the properties of system which are dependent on quantity or dependent on mass or size of the system are called extensive properties, okay. Very, very important. Extensive functions are additive in nature. Additive in nature. Okay. What is that extensive and intensive? I will take one example. With that, you will be easily understanding. Okay. Addition of two volumes of two parts can be possible. Okay. Examples of extensive property. Size depends on the volume, mass, heat capacity. This is total heat capacity. Again, this total word is very important. If I don't use this total word, then meaning will be something else. Okay. Total internal energy is a extensive property. Total enthalpy is a extensive property. Total Gibbs free energy is a extensive property. Total entropy is a extensive property. Number of moles are extensive property. They depend on either mass or they depend on size. Okay. So these are the extensive properties. These are what? Extensive properties. Now I think it is clear to all of you. Now let us see the next slide. Next slide is obviously about what? Very good. Intensive properties. Okay. The functions which are not mass dependent, which are not size dependent. Okay. Quantity, they are not dependent on the quantity, are called as intensive properties. They are not additive. What is that additive? I am taking an example. Let us take. Okay, let us take a container. What is this? Let us take a container. Okay. So listen carefully. This example is very much important to differentiate between intensive and extensive properties. Okay. So as a whole, I am writing the total properties. Okay. So it is 2 liter container. What is this? This is a 2 liter container and 2 kg is the mass. Okay. And temperature is 300 Kelvin. Okay. Pressure inside this is 1 atm pressure. Let us take. Okay. Now after that, what we have done, we have separated it into two parts by using some partition. Okay. This is the partition. Now it is divided into two identical parts. Okay. Now I want information about this part only. Okay. So this part, in this part, what will be? What will be volume? What will be mass? What will be temperature? What will be pressure? So this volume will be how much? 1 liter. Okay. Mass will be how much? 1 kg. And temperature is going to be still 300 Kelvin only. Okay, by keeping a partition, I am not changing the temperature. Pressure also it is still 1 atm only. Okay. So are they depending on quantity or size? No. So they are not mass dependent. Therefore, pressure and temperature. Okay. Pressure and temperature does not depend. I am making 10 parts also. Still temperature is going to be 300 Kelvin only. If I am making 10 parts also, pressure is going to be 1 atm only. But if I am making 10 part, then this is going to be 200 ml. Mass is going to be 200 grams. That lead volume and mass will change. Even density also. See here density is how much? As a total quantity density is 1. Here also density how much it is going to be? 1 only. So density is also intensive property. Okay. So examples are temperature, pressure. There we have taken heat capacity. Now here it is molar heat capacity, specific heat capacity, density, concentration, vapor pressure. Okay, boiling point. Boiling point of 10 grams also same. Boiling point of 15 grams also same. Same way freezing point of 100 kilos also same. Freezing point of 1 kg also same. Viscosity of a substance is same, pH also will be same. So they are all independent of the quantities. Therefore they are called as a intensive properties. And this is one important point, is not additive. Like this density is 1, this density is 1, then density of the total system will be not 2, it is still 1 only. So we cannot add intensive properties. Like here temperature is 300, here temperature is 300, but total temperature will be still 300 only. So never and ever add to intensive properties. That is going to give you the wrong results. Okay. So I think all of you understood now. Make a note of it. Okay, next property is thermodynamic equilibrium. So people are having very wrong concept about the thermodynamic equilibrium. It is not just because of their attentiveness. It is just because, see, thermal equilibrium is different, thermodynamic equilibrium is different. How similarly placed words. Okay. Thermodynamic equilibrium is said to be only when there are three equilibrium coexist. Okay. What is that? Mechanical equilibrium must be there, thermal equilibrium must be there, and chemical equilibrium. When all the three types of equilibrium exist, then only we say that it is in thermal equilibrium, thermodynamic equilibrium. Okay. Thermodynamic equilibrium is the biggest thing. It contains how many equilibrium? Three equilibriums: mechanical equilibrium, thermal equilibrium, and chemical equilibrium. Okay. When there is no change in observable property between the system, when with the over the time, that means pressure remain constant, temperature, volume remain constant, temperature remain constant. Okay. Observable properties of the system, if they remain constant over a period of time, then it is called as a equilibrium. Here we are talking about the system. So that system can be chemicals, that system can be temperature, that system can be a work also. Okay. So that's why if I say thermodynamic equilibrium, it must maintain all the three equilibriums. What are the all the three equilibriums? Mechanical equilibrium, thermal equilibrium, and chemical equilibrium. If one of them also not maintained, we cannot say it is in thermodynamic equilibrium. Okay. For thermodynamic equilibrium, existence of all the three equilibriums are necessary. Now we will study one by one in detail. Okay. This chemical equilibrium is already, there is a chapter already. You might have gone through it. So we will not study much deep into this, but we will study in-depth study about the mechanical and thermal equilibrium. Okay. Note down this. Now let us see the next part. First, let us see about the mechanical equilibrium. Okay. So whether a system is in mechanical equilibrium with surrounding or not, simply we can keep a frictionless massless movable piston over the system. Okay. If it is not moving up or if it is not moving down, it is constant position. What is this? Position is constant. Okay, position is what? Constant. Then we say that it is at mechanical equilibrium. Okay, there should not be any pressure gradient. Gradient means it is not something very difficult word. It should not be vary. Pressure should not vary with time. Okay, pressure should not vary with space. Volume should not change. Okay, there can be uh, pressure gradient with space as a pressure at the bottom of the container in which liquid is filled greater than the pressure at the surface of liquid. That means liquid have the tendency to flow. So that space also should be fixed. Whatever the space it occupied before, and it should occupy for a longer duration. Then it is called as a mechanical equilibrium. Okay. This is about what? Mechanical equilibrium. Now let us see about the next type of equilibrium. Okay, next type of equilibrium will be this one. Thermal equilibrium. So how to confirm whether it is in thermal equilibrium or not? Simply temperature, if it is constant for a over period of time, there the position of piston must be fixed. But here temperature should be fixed. Okay, then it is called as a thermal equilibrium. Then it is called thermal equilibrium. There should not be pressure gradient, then it is mechanical equilibrium. There should not be temperature gradient, then it is thermal equilibrium. Okay, so different places or location must be remain same. Here also, if it is 20 degrees Celsius, here also it should be 20 degrees Celsius. Here also it should be 20 degrees Celsius. Even outside also it should be 20 degrees Celsius. That means they both are in thermal equilibrium with each other. Okay. Next, chemical equilibrium, already concentration of reactant, concentration of product should be constant, not same. Okay. In the equilibrium, concentration of reactant and product must be constant, not same. Then we say there is a chemical equilibrium in the system. Concentration gradation is not there, chemical equilibrium. Temperature gradation is not there, thermal equilibrium. Pressure gradation is not there, then it is called mechanical equilibrium. These are about the types of three equilibrium. When these three equilibrium coexist, when these three equilibrium coexist, then it is said to be in which equilibrium? Thermal equilibrium. Then it is said to be in thermal equilibrium. Okay, so this is about the thermal equilibrium, mechanical equilibrium, and chemical equilibrium, and difference between different types of equilibrium. Okay, main condition, the difference you should know. Okay. Now, types of thermodynamic process, very, very important points. Okay, everywhere numericals, definitely these words are going to be used. Okay, so that's why I am giving you only required information for short and accurate information. Isothermal process. Okay, the process which takes place at constant temperature is called as isothermal. So Ti means initial temperature, final temperature are same. Therefore, delta T will be 0. In any numerical, I will ask you people during the solving of numerical. If I say isothermal, definitely what you can substitute? Delta T is equal to 0. Isochoric. Choric means volume. So volume constant. So V final is equal to V initial. Delta V is equal to 0. Isobaric, pressure is constant. Pi is equal to P final. Therefore, delta P is equal to 0. Adiabatic, that means Q. So, heat is neither lost nor gained. Therefore, heat exchange with the surrounding is 0. Cyclic process. Okay. So, whenever there is a cyclic process means it is going from first to second. Again, it coming back to the same. So delta V will be how much? 0. Like that, all process which are whatever the system variable at 1 will be brought back when it come back to the same states. State functions will be same because it is coming back to the same physical state. Okay, so these are the types of thermodynamic process. Very very important slide. Okay, and indirectly we are going to use them in the numerical. Is that understood? Okay, these are the most important and mostly asked questions about the types of thermodynamic process. Okay, first one is isothermal process, the process which is carried out at constant temperature, that is delta T is equal to 0. Then Iso Choric process, volume is constant, delta V is equal to 0. Isobaric process, pressure is constant, delta P is equal to 0. Adiabatic process, heat change is 0, therefore Q is constant. Okay, or heat given to the surrounding from the system is equal to 0. Next, cyclic process which undergoes series of changes. Here it undergoes series of changes, but there won't be any change in the initial and final state. Okay, final state will be exactly equal to initial state. Okay, so this is about the types of thermodynamic process. Now we will go for the next slide. Okay, next we have done on which parameter is kept constant during a process. Now we are going to do how the process is carried out. Okay, types of thermodynamic process only we have done, but that was on the basis which parameter is kept constant during that. Okay, but here this is the classification, the way process is carried out. Okay, how the process is carried out based upon that thermodynamic process are further classified into two types. Okay, what was the previous classification? That previous classification was based upon what parameters are kept constant during that process. Okay, during that process temperature is kept constant or pressure is kept constant. Likewise, one of the parameter, volume is kept constant, heat is not exchanged, like that, that was parameter based. But here this classification is based upon how the process is carried out. Okay, if the process is carried out small changes. Okay, if the process is carried out infinitesimally slowly, infinitesimally slowly, and process can be reversed at any point of time because the very very small change will be there. It can be reversed back, it can be brought back into the original space by small change. That's why it is called as a reversible process. It can be reversed, okay, at any point of time. So if a process is carried out in such a manner that system is always, this is very very important, thermodynamic equilibrium. Already we have studied thermodynamic equilibrium is not same as a thermal equilibrium. Thermal equilibrium is different, thermodynamic equilibrium is different. Thermal equilibrium is only when temperature is kept constant. Thermodynamic equilibrium contains thermal equilibrium, mechanical equilibrium, and chemical equilibrium. Okay, at every stage of a process, at every stage of process, we assure that thermodynamic equilibrium. Thermodynamic equilibrium is further divided into three types. Okay, so that we have studied already: mechanical equilibrium, thermal equilibrium, and chemical equilibrium. Okay, so if the process is carried out in a reversible manner, all the three equilibrium will be maintained at all point of time. Okay, so this is about the reversible process. Okay, we will study some more points according regarding the classification. Okay, okay, now let us see the thermal uh, thermodynamic process, if it is carried out reversible manner, let us take, this is the equilibrium position. Okay, equilibrium position means pressure by the gas. Pressure by the gas is equal to pressure from the atmosphere. Okay, and apart from that, if it is at this constant position, then pressure of the gas must be equal to pressure by the atmospheric gases, then it is equal to mg, that is mass into acceleration due to gravity per unit area. Okay, a is what? A unit area. So for piston to be in equilibrium, that means this pressure, these are the two pressures acting perpendicular or in the opposite direction. These opposite direction force must be equal to this force. Okay, these two forces are, I will use another color so that it can be understood clearly. See, these blue color circled forces, acting down. Okay, pressure of the gas, which I will use red color so that you can understand. Okay, so this is acting upward. So pressure of the gas is acting upward and these two forces are acting downward. When both forces are equal to each other, then we say that it is at the equilibrium. Okay, so now let us see this graphical representation. This is the initial position, this is the final position. Okay, if it is moving from I to F, initial to final, see here we can say PV diagram, VI and VF, this is the volume. So VF, here we can say that VF is greater than VI. So if it is coming from I to F, VI to VF, VF is greater, therefore it is called as a expansion. What it is called as? It is called as expansion. Okay, but if it moves in this direction, F to I, then it is called as a compression. Okay, so expansion means volume increases. If volume increases, then we say expansion. If volume decreases, if volume what happens? Decreases. If volume decreases, then it is called as a compression. And always make sure that if volume increases, automatically pressure will decrease. You can see here, see volume is lower and pressure is higher. Okay, volume is higher, then pressure will be lower. Okay, pressure and volume are inversely proportional. Increase in volume will automatically decrease the pressure. If you increase the pressure, that means volume is decreasing. Okay, so that relation is already shown here. So during expansion, if you say in terms of the pressure, during expansion pressure will decrease and volume will increase. During compression, pressure will increase, volume will decrease. Okay, this is the graphical representation both for expansion and compression. Okay, I think all of you noting down this. Okay, now let us see the next one. Next one. Okay, that was regarding the irreversible process. Now we will study about the reversible process. Sorry, that was reversible process. Now we are going to study about the irreversible process. Reversible process is carried out. Reversible I am talking about. It is infinitesimally slowly, so that system is always in equilibrium with surrounding. But if the process is irreversible, then it cannot be reversed. There it was, it can be reversed by a small change. But here it cannot be reversed by small change. Okay, it is called as irreversible. The process is carried out in such a manner that system is in thermodynamic equilibrium. Okay, but not at every condition. It is in thermodynamic equilibrium either initially or at final. Okay, in reversible process, the system is in thermodynamic equilibrium with the surrounding at all point of time, but here it is not all point of time. Here but not at intermediate stages. That is the first difference. Okay. Then system may be thermodynamic equilibrium at some finite number of intermediate stages. Okay, it was infinite number at every point of stage it was in equilibrium, but here it is not like that. Okay, it may be in thermodynamic equilibrium for some time. Okay, it is sure that initial stage and final stage it will be definitely in equilibrium, and there are some chances that it may be in equilibrium with finite number of intermediate stages. Okay, so that we are going to study n step irreversible. Okay, so 2 step, 3 step, 4 step. Suppose if it is 2 step, then two finite number. Okay, then during this process, the finite difference in driving force and opposing force is, so that process takes place at finite rate. Okay, so in the diagram I already told you, suppose this is at the fixed position. Okay, so here this is the, suppose during compression this is the driving force. Okay, this is opposing force. When it is during compression, when it is during compression. Okay, so during compression this will become as a driving force, this will become as a opposing force. Okay, now let us see about the next. During intermediate stages of irreversible process, the different state function as such as pressure, temperature are not defined because this will takes place very fast. Okay, reversible reaction will takes place very slowly, so the pressure almost remain constant, temperature almost remain constant, but during irreversible process it takes place so suddenly, even we cannot measure the pressure, we cannot measure the temperature, so it is not defined. Okay, actually all real processes are irreversible, whatever the process we carry out in the labs. Okay, in daily life, whatever the process we carry out, they are all irreversible. Nobody can carry out a process in a reversible way because it is very slow process. Nobody want any process to be very slow. Okay, that is only for ideal, that is only imaginary, but real is irreversible. Okay, so I think all of you noted this. Now let's go for the next slide. Okay, already we have seen the diagrammatic explanation of the reversible process. Okay, now we are going to see about the irreversible process. Okay, consider the system, this system. If a stopper is placed, here this is the stopper placed, okay, over a piston is removed. It is highly compressed and placed stopper, okay. When this stopper is removed, then there will be sudden expansion. There will be sudden expansion. Okay, when piston is removed, sorry, when stopper is removed, okay, then piston will move with a almost infinite acceleration. That means very fast way it will move upwards. Okay, and will keep moving, will keep on moving till what time? When this pressure of the gas will become to the atmospheric pressure. That means final stage will be again at equilibrium. Initial stage was equilibrium because of the stopper. Okay, so the force by the stopper and force by the atmospheric pressure was equal to pressure of the gas. But once this force is removed, then it have to become equal to atmospheric pressure. Then there will be sudden expansion will takes place. Okay, so this is taken place in how many steps? Only one step. Just remove the stopper, it will move fast. Okay, that is irreversible process. Okay, since the process is completed in a finite time, fraction of second only, it will be completed. Okay, so there was a finite difference between the driving forces and opposing force here. For the compression, for the expansion, okay, pressure of the gas is what? Driving force, and pressure of the atmosphere is opposing force. Okay, it wanted to expand this, because of this pressure it was not able to expand. That's why it is called as a opposing force, and it wanted to move like this. So this is the driving force. What is this? This is the driving force. Okay. Driving force and opposing force is understood. And it is not always this atmospheric pressure will be opposing force. Suppose during compression, this will become driving force. This will become compression opposing force. Okay. Whatever the force acting in opposite direction of our required process is called as a opposing force. Whatever the force acting, suppose we wanted to move in this direction. Okay, this is our aim direction. If some force is acting in this direction, okay, if some force is acting in this direction, then it is called as what? Driving force. Okay, and if some force is acting, if some force is acting if some force is acting in this direction, okay, so we wanted to move in this direction, but some force is acting in this direction. So this force is called as what? Opposing force. What it is called as? Opposing force. Okay. So this is the process. Now during expansion, our aim is to move in this direction. During expansion, our aim is to move in this direction. So during this moving, what happens? This force of the gas also, pressure of the gas also in the same direction. That's why this is called as a driving force, and atmospheric pressure is acting in this direction. That's why it is called as a opposing force. Okay, so it is n. Here n means how much? 1. Okay, single step process. In the previous slide I told you n is number of steps. Here only one step, remove stopper, that is the step. Okay, so initially that in the initial previous graph I told you this will be like this. Okay, but in the irreversible process we cannot measure the intermediate stages. There are no definite value of pressure and volume. That's why see, initially we measured pi and vi, and finally only we can measure. We cannot measure p intermediate, v intermediate. Okay, they don't have definite values. Why we don't have? Because the process is very fast enough. Okay, the process is very fast that we cannot measure pressure at any intermediate stage. But in the reversible process, the process was carried out very slowly, so we can comfortably calculate pressure, we can comfortably calculate volume at any intermediate stages. Okay. So only one step it is converted from initial to final. That's why here n is equal to how much? 1. Now n value is it understood? I to F. If it is moving I to F, so volume is increasing, therefore it is expansion. Okay. And F to I, so volume will be decreasing, then it is called as a compression. So this is the graphical explanation of the irreversible. Both graphs I think you are understood now. In the reversible graph you will find a curve like this. You will find a curve like this because we can measure the pressure and volume at every stage. Okay. Is it understood now? Okay. Now let us see the next slide. What we will see now? Let us see the next slide. Okay, now very important for the numerical part. As of now, we have studied a simple theory part. Okay, so modes of exchange of energy. Okay, once I say exchange, there will be one will be losing, one will be gaining. Okay, so that means there should be how many people must be there? There should be how many people for exchange? Minimum how many people must be there? Minimum how many people must be there for exchange? Okay, modes of exchange of energy. For exchange, there should be two things. There should be two things minimum. What are those two things? One is called as system. One is called as system. Okay. The exchange will be between how many people? Two people. One will be called as system. Another people is called as surrounding. Another people called as surrounding. Okay, so the exchange between system and surrounding will be energy will be exchanged. Okay, Energy exchange is possible in which type of system? Open system, closed system, isolated system. Very good. Energy exchange is possible in open system and closed system only. Isolated system, there is no exchange of energy. Okay. So how they exchange energy? They can exchange energy in the form of heat also. They can exchange their energy in the form of work also. Okay. Heat and work both are forms of energy. So why this sentence I am more emphasizing, because work also form of energy, heat also form of energy. Therefore, their units also will be same. Okay. What units will be same? Energy units, work units, heat units will be same. What are the units? Joules or kilojoules. Okay. Joules are kilojoules. Calorie, calorie or kilocalorie. Okay. Calorie or kilocalorie or another type of what is the energy? Erg also. These are the some energy units. So we can use the same units for the energy also, for the work also, and for the heat also. Okay. So heat, when the energy transfer across a boundary, what, how many types of boundaries are there? Already I have explained. As a result of temperature difference between the system and surrounding. Okay. So out of this, when heat will be transferred, when work will be transferred, when there is a difference in temperature between system and surrounding. Okay. I will try to draw a beautiful diagram here. This is a cylinder. What is this? Very good. This is a cylinder. Okay. Now it is fixed with the frictionless piston. Fixed with frictionless piston. Okay. Now when it is compressed or expanded, suppose there is a temperature T1 and temperature T2 and they are composed of diathermic walls. Which thermic walls? Diathermic walls. Okay. Suppose T1 is greater than T2, then what happens? Heat will be moving out from the system to surroundings. Okay. Suppose another condition, when T1 is less than T2, okay, that time heat will be flowing. So if both are same, then there is no chance of the heat flow. Okay. Mode of transfer of energy are how many types? Two types, work energy and heat energy. When there will be heat form? Only when there is a temperature difference between temperature of system and temperature of surrounding. Okay. So when both temperatures are same, then we don't opt for the heat as a mode of transfer of energy. That time what we will go for? We will go for the work energy. Okay. And work energy, how it is going to be there, that we are going to study now. Okay. So modes of heat of transfer. Okay. Heat also can be transferred from system and surrounding in how many ways? Three different ways. Okay. So this you will study more easily in the what? Physics. Heat can be transferred from system to surrounding due in the conduction. Okay. This is found in the solids, and convection in the fluids, radiation in the vacuum. Okay. Heat will be transferred when temperature difference is there between the system and surrounding. But the way of heat transfer also from the system to surrounding, way of heat transfer also how many types? Three different ways. If both are solid, between the solids, the heat transfer will be due to conduction. If liquids, heat transfer will be due to convection. If it is in vacuum, then heat transfer will be due to radiation. So modes of heat exchange between system and surrounding will be how many types? Three types: conduction, convection, and radiation. These are the three types. Okay. Now this is about the heat transfer. Heat transfer will takes place, condition of heat transfer, temperature change. Way of heat transfer, conduction, convection and radiation. Okay. Now when we will opt for the work energy, the energy transfer which is not heat or which is not because of the temperature is called work. Okay. Whatever the heat energy transfer not because of the temperature, that all energy transfer is called as a work transfer. Okay. So here like heat transfer are conduction, convection, radiation. Same way work can be mechanical work, electrical work, magnetic work, gravitational work. Okay. But in this chapter, we are going to study mostly mechanical work. For the electrical work, we have a separate chapter, electrochemistry. Magnetic work you may study in physics. Gravitational work you may study in the physics. Okay. Here we are going to study, concentrate on the mechanical work. Okay. So, like heat transfer are how many types? Three types: conduction, convection, and radiation. Work transfer are mechanical work, electrical work, magnetical work, gravitational work, and so many types are there. But don't worry about all of them. For better score, you should worry about mechanical work only. Okay. So the same energy transfer can be called work, can also be called as a heat. Okay. So it is not that if exchange is taking place heat, then energy will be more or work energy will be less. It is not like that. Energy will be same whether it is carried out, whether it is exchanged in the form of the work or it is in the form of the heat. Let it be any form, energy will be same. Okay. So this is about the difference between the heat transfer and work transfer. Okay. So this is the where people are lagging, people are confusing. What is that sign convention? What is that sign convention? Okay. Where to write negative, where to write positive. Okay. So because there are a lot of confusion according to chemistry and according to physics. Okay. So for that part only I wanted to combine both of them together and so that you should not have any confusion. Okay. So physics somebody says it is plus and chemistry somebody says minus. So that's why for chemistry, till the time you are attending questions from the chemistry, whatever the sign convention I am giving you in the chemistry side that you should follow. Okay. So IUPAC sign convention about heat and work. Okay. Heat taken out from the system. Okay. First, any energy given to the system taken as positive. Okay. So heat is given to the system will be positive. Heat given to the system will be positive. Then heat taken out from the system will be automatically negative. Okay. So think as if you are the system. If something is going out of your pocket, that means it is reduced, so negative. Same way work done on the system will be positive, work done by the system will be negative. Okay. So this is IUPAC, this is applicable for what? Chemistry. Okay. Chemistry you will follow this convention. Okay. Suppose work done on the system, then it will be positive. Work done by the system, negative. Heat given to the system, positive. Heat given out by the system, here it is actually Q. Okay. Q means heat. Is it understood? Okay. Now let us see, sign convention is different from physics, but meaning always comes out to be same. Okay, only in equation we have to use different sign convention. Okay, suppose if any problem, work is minus 10 joules. Okay, it means work done, where system has done work of 10 joules on the surrounding. Minus, so minus means work done by the system on the surrounding. Okay, so this is what the, according to chemistry, delta Q and delta W, work done and heat given to the system. Then this is the formula for the chemistry. Okay, IUPAC convention of heat. Heat given to, this is the work convention, this is the heat convention. Heat given to the system will be positive. Work done on the system will be positive. Okay. But according to physics, this you will follow. Okay. So you worry about and follow in the chemistry exams this part. Okay. Chemistry exams you will follow this convention, sign convention. Is that clear? Okay, now let's see about the zeroth law of thermodynamics. Okay, so in future, if I write ZLOT, you should understand. Short form I will be using ZLOT, zeroth law of thermodynamics. Okay, so here I am taking how many systems? Two systems. Okay, so system A is in thermal. See here, it is not thermodynamic, my dear students. Okay, system A is in thermal equilibrium with B. System A is in thermal equilibrium with C. Separately, then they themselves also will be in thermal equilibrium. Thermal equilibrium means temperature will be same. If these two temperatures are same, these two temperatures are same, automatically these two temperature also will be same. Okay. So if two system are in thermal equilibrium with the third system, like B and C are the two system, third system is A, then they are also in thermal equilibrium with each other. This is zeroth law of thermodynamics. Okay. So note down this law and we are going to start now with the next law or next topic. Okay. Okay, next is what? After zeroth, automatically you should understand first law of thermodynamics. Okay, first law most of the students already studied, but they don't know that that is only first law. Okay, first law already studied as law of conservation of energy. Okay, whatever the law you have studied as law of conservation of energy, here it is same. Okay, energy of total universe is always conserved, or total energy of an isolated system. Already yesterday I have given you in the note, total universe is an isolated system. Okay, if energy, what do you call isolated system means it cannot exchange heat, it cannot exchange energy. So it is always conserved. Okay. So hence absolute value of E can never be calculated but can only change. Here he is, E is internal energy, can be calculated for a particular process. Okay, actually internal energy is many type of energies. Okay, translational energy. Okay, here E means what? Internal energy. E is internal, internal energy. Okay, so internal energy is sum of the translational energy, vibrational energy, mechanical energy, electrical energy, okay, and so on, so on, so on. So many energies are combinedly called as a internal energy. So we can never calculate absolute value, okay, but we can calculate change, okay. We cannot calculate E value. Can we calculate E? No. But what we can calculate? We can calculate delta E. Delta E we can calculate, but not E. Okay. Now, mathematical form of the float. Float means first law of thermodynamics. Okay. So, a system is initially having internal energy of E1. Initially, which have a total internal energy is how much? E1. Okay. Now, to that Q amount of heat given will be plus. Okay. Heat given will be plus. And W amount of work done on it, work done on the system. So plus. Okay. Initially it was having E1. Heat is given to the system plus Q. work done on the system plus W. So total energy after all this process is E2. Okay. So E2 minus E1 is equal to Q plus W. Okay. So the first law of thermodynamics says that delta E is equal to Q plus W. This is the mathematical form of internal energy change. What is that? Delta E is equal to Q plus W. Okay. Okay, now let us study about the first law of thermodynamics uses. Okay, what is the first law? Very simple, energy is conserved. Conserved means it will not change, it will not increase. Energy will not increase, energy will not decrease. Okay, so here delta U, formula of the first law of thermodynamics. Delta U is equal to delta Q plus delta W. Okay, this formula we will derive, don't worry. But for the safe side, I am teaching you here itself. Delta W is equal to minus P delta V. Okay. So minus P delta V, if I substitute here, then I will get another formula. Okay. And this P must be external pressure. What is this P? P is external P is external pressure. Okay. Now calculation of different quantities of first law of thermodynamics. Okay. What are the quantities we are dealing with? Internal energy delta U and delta E both are same. Don't worry. That is what it is mentioned here also. Okay. E also denoted by U. Okay. How to calculate delta E, how to calculate delta Q, and specially we will focus on calculation of work, okay, in different forms. Already this I have told you, internal energy. Every system has some quantity of matter associated with the definite amount of energy called as internal energy. Like every mobile nowadays comes with some internal memory. Okay. So likewise every system by birth, by virtue of it, it is going to contain some energy. That energy is called as what? Internal energy. That energy is called as what? Internal energy. Okay. As such, immediately once system is formed, it is going to have some energy. That energy is called as internal energy. Actually, internal energy is a sum of translational energy, okay, rotational energy, vibrational energy, bonding energy, nuclear energy, likewise. Okay, but it is not possible for any human being to calculate translational, rotational, vibrational, bonding and all. So we cannot calculate absolute value of E, but we can calculate delta E, change in internal energy we can calculate, which is equal to final minus initial. Is it understood? Note down this. Okay, now this is about the internal energy. Now let us see the next slide. Thermodynamic definition of an ideal gas. Thermodynamic definition of ideal gas. Okay. Actually, this is a topic of states of matter, but I take this opportunity to cover the gaseous state also. Okay. For a gas, the internal energy is directly proportional to absolute temperature. Okay. That means temperature is directly proportional to E. That means temperature depends only on internal energy. Then only it is called as what? Very good. Then only it is called as ideal gas. Otherwise, no ideal gas. See, delta E divided by delta V at constant temperature. Temperature is constant. Then internal energy change also constant. That is zero. Okay. So you change pressure, but temperature is constant. Delta E will be zero. That means delta E will change only and only with temperature. Then it is called as a ideal gas. Okay. So here if delta E is QV, V is what? V stands for, here it is not velocity. It is for the volume. It is for what? Volume. Okay. So constant volume. since all heat supplied goes to increase internal energy only. Okay. So if anywhere we get QV, so blindly you can take this in the formula as delta E. What you can take it as? Delta E is also sometimes called as delta U. Okay. Delta E and delta U are both are same, equal to QV. What is QV? Heat, already it is given. Okay. Heat at constant volume. Okay. And sometimes we will enthalpy also we will study QP. Okay, what will be its name? Heat at constant pressure is called as delta H. Delta H is called as enthalpy. Okay, what is delta H? Enthalpy change. So people were asking and very worried about enthalpy. Enthalpy is simply heat exchange between the system and surrounding at constant pressure is called as enthalpy. Heat exchange at constant volume is internal energy. Okay, so it is an extensive property. Extensive and intensive already we have studied, and it is a state function. State function and path function also we have studied. That's why I told you to be attentive at every point of time. Okay, if you miss one point at some initial stages, then it is going to affect your understanding in the future classes also, future lecture also. Okay, so that's why state function means it depends only on initial and final state, but not way it used to reach that. Extensive means it depends on the quantity. Intensive means does not depend on quantity. Okay, it is exclusively function of temperature. That means internal energy will change only if temperature is changed. Okay, so if delta T is equal to 0, delta E will be 0. Delta T is positive, delta E positive. Delta T negative, delta E will be negative. Okay, with temperature change only, kinetic energy changes. Okay, temperature change will cause the kinetic energy change. Kinetic energy will change will cause the internal energy change. Okay. Okay, students. Now we are going to start with the degree of freedom. Okay. Actually, this is a topic of the physics. You will study in detail in the physics, but still I will have a look on this. Okay. After some slides, I will give you the shortcut table. Okay. After some slides, what I will do, I will give some shortcuts of the degree of freedom. Okay. So degree of freedom is total number of modes which on which a molecule of an ideal gas. Okay. In the previous slide only we understood how many modes of ideal gas, what is the ideal gas. Okay. In the thermodynamics, there is a different definition. Ideal gas states of matter definition is different. Thermodynamics ideal gas different definition is different. Okay. So previous slide only we have defined. If you got any problem, pause the video and go back. Then you can check it again. Okay, because in thermodynamics continuity is very much required, and attentiveness from the beginning to the end of the session, you should be very attentive. If you miss one or two points, that time you may not be able to understand its intensity, but slowly that doubts will keep on accumulate, and they you will not be able to understand the actual concept. Okay, so can exchange energy during collision is known as degree of freedom. Okay. Degree of freedom is simply number of modes. Okay. The molecule of ideal gas can exchange during collision. During collision, how many types, how many modes it can exchange. Okay. So the first type which we are going to study is translational degree of freedom. Translational means moving. Okay. So let us take, this is the x-axis, this is the y-axis, and this is the z-axis. So for all type of gases, for all type of gases, One degree will be x-axis, another degree will be y-axis, another degree will be z-axis. Okay. Translational means moving the gas. Okay. Gas can move in which directions? Three directions it can move. X-axis, y-axis and z-axis. That is called as a translational degree of freedom. Okay. Rotational degree of freedom. Rotational degree monoatomic. Okay. If only one like helium or any monatomic gases are there, then for them there is no direction. Okay. So diatomic, suppose diatomic and linear gas. Okay. Suppose Cl and Cl. Okay. So if it rotates, this total degree will be how much? 180. Okay. So this is the 180 and total angle is 360. So the rotational degree of freedom will be how much? 2. 360 by 2. How you got this 3? 2, I think it is understood. Angle between the bonds are 180 and total permitted angle is 360. Same way, non-linear polyatomic gases. Okay. Simply polyatomic gases, it will be 3 degree and it is 120. Okay. So total 360 degrees covered by 120 angles. Okay. So there are two types of degree of freedom: translational degree of freedom, rotational degree of freedom. Okay. So when you add both of them, suppose for monoatomic, suppose for what atomic? Monoatomic, 3 plus 0. 3 plus 0. Degree of freedom will be how much? 3. Okay. For diatomic or linear polyatomic. Okay. So 3 plus 2, how much it is going to be? 5. And for non-linear polyatomic, 3 plus 3, how much it is going to be? 6. So this is called as a degree of freedom. Degree of freedom is number of modes on which molecule of ideal gas can exchange energy, but not every time, during collisions. Okay. During what? During collisions, number of times it can, number of ways, number of modes it can exchange energy. Okay. So that is called as a degree of freedom. Is it clear to all of you? So these are the degree of freedom: total, translational degree of freedom, and rotational degree of freedom. Rotational degree of, next about the triatomic. Okay. Next about what? Triatomic. Is it understood now? Let us see about the next slide. Let us see about the next slide. Next, law of equipartition. What is the next topic? Law of equipartition. So this law of equipartition, very simple. Energy equal to 1 by 2 kT. Energy equal to 1 by 2 kT is each of the degree of freedom per ideal gas molecule. Okay. What is K here? K is a Boltzmann constant. Understood? K is a Boltzmann constant. And here F is the degree of freedom. Okay. What is F? Already I told you in the previous slide. F we will learn. We have learned in the previous slide. And when you multiply it with 1 by 2 kT. Okay. Actually, K is equal to what? See, K is equal to R upon Boltzmann constant is universal gas constant divided by Avogadro number. Boltzmann constant is universal constant, universal gas constant divided by Avogadro number. Okay. So very simple. Energy of every ideal gas F by 2 nRT. If number of moles are given, you will use this formula. If change in temperature is given, you will use this formula for change in energy during collision. Okay. For n moles, these are the three formulas. For 1 mole, that means n is equal to Avogadro number. So F by 2 RT. Okay. What is F here? Degree of freedom. What is K here? Boltzmann constant. What is R? Universal gas constant. For energy, F by 2 nRT. For change in energy, then the F by 2 nR delta T. Okay. So very important formula, especially if you are aspiring for advanced only. Okay. This is not required for those people who are aspiring for mains. Okay. I think it is clear now. Let's go to the next slide. This is law of equipartition energy is applicable. Law of equipartition energy is applicable with respect to degree of freedom, with respect to Boltzmann constant, with respect to number of moles, with respect to change in temperature. Okay. These are the things on which law of equipartition works. Law of equipartition works. Okay, next topic is heat capacity. Topic is heat capacity. Heat capacities are divided into three types. Heat capacity is divided into how many types? Three types. Okay. First one is total heat capacity. Second one is specific heat capacity. And third one is molar heat capacity. Okay. Total heat capacity, molar heat capacity, specific heat capacity. Total heat capacity means nothing is mentioned. It is not per gram, it is not per mole. Then it is called as a total heat capacity. Okay. Now heat capacity word will be same everywhere. Heat capacity is basically heat required. Heat capacity is basically what? Heat required. Heat required. Heat required. Heat required to raise the temperature of a system by how many degrees Celsius? 1 degree Celsius. Okay. Now, but here nothing is mentioned how much it is. Whether it is 1 mole, whether it is 10 moles. Number of moles are not mentioned. Mass is not mentioned. Then it is called as a total heat capacity. What it is called as? Total heat capacity, and it is denoted with CT. What it is denoted with the CT. Okay. And formula will be change in heat required for the change in temperature. Suppose for a system, on a system, I given 150 kilojoules. How many kilojoules? 150 kilojoules of heat for, which changed the temperature by 3 degrees Celsius. Okay. Change in temperature is 3 degrees Celsius. Heat given to the system is how much? 150. Then what is the total heat capacity? Okay. Question, is it understood? Okay. Heat capacity is the amount of heat required to change the temperature of a given substance or a system by 1 degree Celsius. Okay. Amount of heat required to change or increase the temperature by 1 degree Celsius. That is called as a heat capacity. Heat capacities are divided into three types. Divided into how many types? Three types. First one is called as a total heat capacity. Here there is no restriction of mass. There is no restriction of mass. There is no restriction of moles. Okay. Let us take, for example, 150 degrees Celsius. Sorry, 150 kilojoules of heat. How many kilojoules of heat? 150 kilojoules of heat I have given. Then it caused the change in temperature by 3 degrees Celsius. Okay. What is the total heat capacity? It is very simple question. If 150 kilojoules of heat given to the system caused the temperature increase by 3 degrees Celsius, then what is the total heat capacity? Total heat capacity is amount of heat required to raise temperature of 1 degree Celsius. Question, I think it is clear to you. Now I will look into your answer. Yes, very well understood. For 3 degrees Celsius, if it is 150 kilojoules, then for 1 degree, obviously, how much it is required? 50 kilojoules is required. So that's why, see, amount of heat required by change in the temperature is called as a total heat capacity. Total heat capacity, I think it is clear now. Now let us see about the next slide. Okay, let us see about the next slide. Okay, now extensive property. This total heat capacity is a extensive property and path function. It depends on how it is obtained. Okay, and also it depends on the quantity. That's why it is extensive property. Okay, so if small changes if it is done, then integration we will do. Okay, dq by, very important formula for total heat capacity. Total heat capacity, if you are given with, you will find out the q. Okay, q is the amount of heat required for 50 degrees Celsius, 10 degrees Celsius. This is the formula. Then molar heat capacity, nothing new, everything definition is same, but you have to make sure that it should be calculated for 1 mole only. For how many moles? 1 mole only. Okay, see, every formula is same. What is the extra term introduced here? N is introduced. Okay, so q is the heat required equal to n into, because for 1 mole it is cm. Actually we will write with the capital C. Okay, there are further divided into two types, cp and cv. Okay, so c is the here molar heat capacity and dt is the temperature change. dt is what? Temperature change. Q is equal to n into c into dt. If you understand this, then you can write it for every formula. Okay, now here it is per mole. Here it is for how many moles? Here it is for per mole. That's why it is a intensive, and still heat is a path function. Okay, if molar heat capacity at constant pressure, what is this? Constant pressure, okay, is denoted with Cp, and constant volume it is denoted with Cv. So let me introduce you heat capacity. I will write summary of this. Heat capacity basically divided into how many types? Very good. They are basically divided into three types. Okay. First one is total heat capacity. First one is total heat capacity. Second one is molar heat capacity. Then it is specific heat capacity. Oh shit. Specific heat capacity. Okay. Molar heat capacity is further divided into two types, Cp and Cv. Cp is the molar heat capacity at constant pressure. Cv is the molar heat capacity at constant volume. Okay. So simple, if you understand the molar heat capacity, the same thing will be applicable for the uh, specific heat capacity, but there we will mention as per gram. Instead of 1 mole, what we will mention? Per gram. Okay, so everything is same, so need not to worry much. So here I am writing here. Okay, there it was number of moles. Actually here we will denote it with the S. Okay. So three things. Ct is the total heat capacity. C is the molar heat capacity. S is the specific heat capacity. Okay. C is further divided into two types, Cp and Cv. Okay. And this is a extensive and this is intensive. This is also intensive. Okay. Intensive path function. Specific heat, again, this is also divided into how many types? Two types. Okay. SP, specific heat capacity at constant pressure, specific heat capacity at constant volume. Okay, and intensive but not path function. Okay, S is a path function, But SP and SV, because path is already mentioned here, pressure is constant, volume is constant, therefore they are not path function. Okay. Now let us see the next topic. Heat capacities, I think it is clear because it is almost everywhere required. Okay, now let us some additional topics related to our heat capacities. Okay, total heat capacity, molar heat capacity, and specific heat capacity. Most of the time you will be given with one value and you have to find out another value. So that time interrelation, interconversion is very must. Okay, interconversion is very must in that condition. So let us see, if you are given with total heat capacity and you want to find out molar heat capacity, very simple, N into C, you will get the total heat capacity. Okay. And if you are given with specific heat capacity, S is what? Specific heat capacity. When you multiply it with mass, then you will get total heat capacity. Okay. Total heat capacity can be obtained both from the molar heat capacity. When you multiply it with mole, you will get total heat capacity. Specific heat capacity, when you multiply it with mass, you will get total heat capacity. Understood? So simple, everything is written here. For isothermal process, isothermal means simple, delta T is equal to 0. In the denominator, delta T is equal to 0. Then something upon 0 will be infinite. Okay. For isobaric process, it is already told C is equal to Cp. P shows that pressure is constant. For isochoric, this already types of process we have already studied. Isobaric, pressure constant, isochoric, volume constant, isothermal, temperature constant. And adiabatic, what is adiabatic? What is adiabatic? The process in which heat exchange is not there. So once you are not giving any heat, then C will be 0. Okay. So this sentences will be given in the exam through in the question, and these things you are permitted to substitute. Okay. Next, heat capacity is a path function and different type of heat capacities are defined. Okay. Then remember that heat capacity of a substance is not fixed. It is depends on the type of process. So, for the same substance, Cp will be different, Cv will be different because path is different. Here we are giving the heat at constant pressure. Here we are giving the heat at constant volume. Okay, is that clear now? Now let us see the next topic. Work done. Different types of work done we are going to study. Okay, work done. Energy that is transmitted from, what is work? Transmitted from one system. Oh, sorry. Okay, energy that is transmitted from one system to another system, such that difference of temperature. If temperature is different, then automatically mode of transference of energy will be heat. Okay, so here temperature difference is not directly involved, then that mode of transference is called as a work. Work is basically mode of transference of heat. But what is the condition? Temperature should not be directly involved. Okay. And it is a path function. Okay. What is the opposite of path function? Very good. Good. So path function and state function. Opposite of path function is state function. Opposite of extensive property. What is the opposite of extensive property? Yes, intensive property. Okay. If it depends on quantity, then it is called as extensive property. If it depends on path, then it is called as a path function. If any function which is independent of path, then it is called as state function. Any function which independent of quantity, then it is called as any function which is independent of quantity, then it, as far as the work is concerned, it is a path function. That means it is not a state function. Okay. So this definition is consistent for understanding work as force into displacement. Okay. Here force can arise from any type of force, electrical, magnetical, gravitational. That's why work itself are divided into many types. Okay. Heat transfer is divided into how many types? Heat transfer is divided into how many types? Three. What is that? Conduction, convection, and radiation. Okay, like that, work transfer will be electrical work, magnetical work, gravitational work, or mechanical work, and some other also possible. Okay, see, already I told you that previously they both are modes of energy only, therefore their units also will be same. So what are the units? Joules, okay, and some calories, okay. So this is the interconversion. This is very, very important. I hope everybody will write this at least 5 times. How many times you will write? 5 times. If you write, then it will be easy to remember. Okay. You will be given in work formula. I will tell you formulas, especially like work is equal to minus P into delta V. What will be there? P into delta V. So this is liter atmosphere you will get. Okay. So when work calculated is in liter atmosphere, if you wanted to convert into joules, 1 liter atmosphere is equal to 101.3. 101.3 joules. Okay. Or if you wanted to convert into calories, this is the formula for conversion. In the numerical, it will be very, very useful. Where it will be very, very useful? In the numerical, it is very, very useful. Okay. This is the interconversion of one energy. And you are having calorie, you can convert into joules by using this. If you're having joule and you wanted to convert into calorie, you can use this relation. Liter atmosphere, joules and calorie conversion formulas. Okay. Note down this and try to write 5 times today itself, now itself, after the lecture. Okay. So let us see the next slide. Next slide is about the irreversible work. Next slide is about what? Irreversible process. State parameter. Already reversible and irreversible we have done. Okay. State parameters. State parameters such as pressure, temperature cannot be defined because there will be sudden change. Irreversible process, what happens? Pressure will, work will be done. Just this example I have given you, one piston is compressed and placed and stopper, there is a stopper. So when you open it, it suddenly expands. So we don't have time to calculate pressure and temperature. Therefore, it cannot be defined. But work is energy theorem. We can find out. Okay. So work done by the gas. Work done by the gas is equal to work done by the external, that is surrounding. They both will be opposite because work done by the system, if it is positive, work done on the surrounding will be negative, plus delta K into piston. Okay. So once it comes to the rest, that means it is moving, but as soon as both pressure are same, then it will come to the rest. That time delta K piston will be 0. So that means work by the gas is equal to minus work. This is 0 now. Now external work is equal to minus P delta V. This is what I told you. Very, very important formula. Work done is equal to minus P external in delta V. Okay. If this delta is very, very small, then we will integrate. See dV integration. Okay. Very important formula for work. But what the students are doing, They are just multiplying this and leaving as it is. That's why their score is not good. That is what the difference from the reading from the books and getting explanation from the experienced faculty. Okay. So here units will be what? Liter. Pressure, volume will be in liter and pressure is in atmosphere. So units of the work we are going to get will be in the liter atmosphere, but your option will be given either in joules or calories. So by using that chart I have given you for conversion, you should be able to utilize that. Okay, then only you will be able to calculate. Understood? So work done for a irreversible process. What is the formula? Work done for a irreversible process will be, this is the formula. Okay, first formula understood. Now work done in a isothermal expansion, that is also reversible. Okay, so if you are not interested about the derivation, don't worry. At least I expect all of you to remember the formula for each and every work at least. Okay, for irreversible process, work done is equal to minus P delta V. Okay, so work done, since process is isothermal. Isothermal means what is constant? Pressure constant and ideal gas. So PV is equal to nRT we can use. So according to PV is equal to nRT, we can write P is equal to nRT by V. Okay. So this is general formula for work everywhere. So in place of this P, what I can write? P and delta V. V initial to V final. Okay. V initial to what? V final. So in place of P, I am substituting this total nRT in place of the P, then work done will be minus nRT by V, Vi to Vf. This is constant. Why? Because it is isothermal and R is a constant since childhood. Number of moles also constant. So only variable will be 1 upon V. I think all of you are aware 1 upon X, integration of 1 upon dx is equal to 1 upon x dx is equal to what? Integration of 1 upon x dx is equal to what? Very good. Ln x. Okay. This is the integration formula. Understood? So here this is constant. I can write it before. And one integration of 1 upon v dv. Here in place of x it is v. In place of x it is v. So ln v. Understood? And but in India we don't use the, in India we don't use what? Ln. So what that time we will simply multiply. Okay. So work done is equal to minus 2.303 nRT. Now we can write it as a log. Okay. Log V final divided by V initial. This is the formula for work done. This is the formula for work done during isothermal expansion of ideal gas. See why I am specifying, because see here isothermal, that's why I have not integrated the T, and ideal gas, that's why I have used PV is equal to nRT. This formula is derived by using both condition. Therefore both condition must be satisfied for using this formula. Okay. Now this is the graphical explanation. So it will be very, very slowly. Okay, this is the graph representation of isothermal reversible expansion of ideal gases. Okay, so this formula you will remember. What you will do, you will remember for the three condition. First of all, what must be there? Isothermal must be there. Okay, second word we should mention is reversible. Okay, and third word you should use is, remember, is ideal gas. Okay, ideal gas because we are using ideal gas formula. Isothermal because we are not integrating. Reversible because, see, in the reversible process only system pressure, surrounding pressure will be same. Okay, So that's why these three words are very, very essential for utilization. Okay. Now let's go to the next chart now. It's time for the next chart. This is the explanation, practical explanation. Okay. So this will be more useful when you carry out this experiment. Okay. Always one general formula you will remember. What is the general formula? Work done is equal to area under the PV diagram. Work done is equal to what? Area under the PV diagram. Okay. So like in the previous one, we have seen that this is the graph. Okay. So what you will do, this area you will calculate. Okay. So whatever the area, that itself is equal to work done. Work done is equal to area under the curve. So now what they will do, suppose they will ask what is the work done. Okay. Here it is V, here it is P, like that PV graph will be given. So this area you will calculate. Then that area itself is work done. Okay. Area under the curve is called as a work done. Very important, and lot of numericals will be there based upon this simple to simple graph. Okay. Now let's see the next one. Irreversible isothermal expansion. Here, what is the new condition we are going to follow here? Irreversible. Previously it was reversible, but now it is irreversible. Irreversible means sudden. Okay. See, there it was, the variation was like this. Now it is initial and final. There is no line, there is no contact. Okay. It will happen directly, it will happen all of the sudden. That's why it is called as a irreversible. We cannot have the control at the intermediate stages. Here, how you will calculate? Simply area under the curve. What you will calculate? Area under the curve. This is the experimental diagram explaining the irreversible process, and here it is the graphical representation of irreversible isothermal. Still temperature is same, but what is happening? The process is carried out very fast. Once it is carried out very fast, we cannot use the curvy liner. It will be a straight line like this. Okay. Okay. Now let us see the next one. What formula you will use for irreversible isothermal expansion? Irreversible isothermal expansion. Okay. This is the formula. Now let's see the next one. These are all formula, at least if you remember, that is more than sufficient. Okay, two-step isothermal expansion. Actually, reversible isothermal expansion is infinity times. Okay, and if it is same thing is carried out in two steps, that means instead of directly coming from VF2, sorry, very bad. VI2, instead of coming from VI to VF, first VI2 we will go to the V1, then V final. So two irreversible process are combined together, then it is called as a two-step isothermal process. Okay. If we are going through the n step, okay, let us take VI, V final. If you are directly going, irreversible process. If you are slowly going, reversible process. If we take through the V1, then it is called one-step process. If we take to the V1, then it is V2, then it is VF. Now, can anybody tell me and which step process it is? It is which step process? Very good. Three-step expansion. Okay. Here, this is the first step. This is the second step. This is the third step. Like that, n steps, if you are adding all of them, automatically irreversible will be converted to reversible expansion. Okay. But isothermal is still utilized. What is utilized? Isothermal is still utilized. N step I have covered. Okay, this is C. First we are using mass m0, then we are using mass m1. Here also we can say graphical explanation. This is for the first step. This is for the second step. That means it is taking place in how many steps? Two steps. Vi to V1, V1 to Vf. Okay. So in the first step, work done is W1. In the second step, work done is W2. Okay. Like this, if I keep on adding n number of steps, then that work will become as a irreversible, will become as a reversible process. What it will become? Reversible process. Okay. Now let's see the next one. This is irreversible expansion, but n means infinity. So when irreversible process is carried out n number of infinity, that itself will become as a reversible, and reversible formula already I have told you, 2.303 nRT log V2 upon V1, or V final minus, sorry, V final upon V1. Okay. That is the nth step process. That is what? Which step process? N step process. Okay. So when n tends to infinity, that means it is doing infinitesimally slowly. So the reverse irreversible process will become as a reversible process. So same formula we can use. Okay. W is equal to minus 2.303 nRT ln. And already I told you, if it is ideal gas, we can use the PV is equal to nRT. So V2 by V1 can be represented as P1 by P2 also. Okay. I think it is clear now. Okay, if it is isothermal expansion and compression, there is no problem. There is a problem with only final and initially. Automatically, that will be utilized here itself. This will automatically come out to be positive because already minus sign is there. So during compression, final volume will be less, initial volume will be more. Okay, reversible iso, same formula which is applicable for isothermal reversible expansion of an ideal gas is applicable here also. Okay.